All right, so the next thing we're going to look at is another application of Rolle's theorem. I guess it's really the first application of Rolle's theorem that we looked at, so I shouldn't say another. What we're going to do is show that this equation, x cubed plus e to the x equals 0, has exactly one real solution. Now, we can start by showing that it has at least one solution by applying the intermediate value theorem. So if we let f of x equal this left-hand side, x cubed plus e to the x, so defining that as a function. Then we can evaluate f at a couple of different values. And if you remember, what we're looking for is a 0 of this function. So we're looking for a value of x that you can plug in and have this equal 0. I'm not going to be able to find that value explicitly, so instead I just want to show that such a value has to exist. And the intermediate value theorem is how we did that back in chapter 2. First of all, this function is continuous. It's specifically continuous everywhere because x cubed and the exponential function are both continuous functions. And so the sum of those functions would be continuous as well. And the reason that's important is because the intermediate value theorem can only be applied if this function is continuous on some particular interval. It's continuous everywhere, so it's automatically going to be continuous on any closed interval I pick. I'm going to select one. I'm going to say it's continuous on -1, 1. Again, if it's continuous everywhere, it has to be continuous here. Why am I selecting the interval -1, 1? Well, because I worked ahead and I found that if I plugged -1 into this function, and you would use a calculator for this, just it's not a function that's easy to evaluate by hand. But in a calculator, if I evaluated that, I get something that's approximately equal to -0.632. And if I plugged in if I plugged 1 into this function, I get a value that's approximately 3.718. Now, the numbers themselves are not that important. It's more the fact that one of them is negative and one of them is positive. The intermediate value theorem says that because I have a negative number here and a positive number here, then there has to be some value, which we can call c, between -1 and +1, such that f of that number, f of c, is equal to 0, because 0 is between these two values. In fact, I could pick any other value between -0.632 and +3.718 and say that there's a value c in here such that f of c equals whatever that value is. But we only really care about the 0. So I can say by the intermediate value theorem, there exists a number c in the open interval -1, 1, such that f of c is equal to 0. So what that tells me is that there's at least one value that satisfies this equation, because if f of c is equal to 0, then that means plugging c in for the x on this side satisfies that equation, since it's equal to 0. However, the intermediate value theorem does not say that this is the only value of c for which this is possible. It could be that there's several values of c in between -1 and 1, such that f of c is equal to 0. In fact, it may also be the case that there's other values of c outside of this interval that also satisfy that equation. So the intermediate value theorem is not enough to fully answer this question, because we need to know that there's exactly one solution, not at least one solution. This is where Rolle's theorem comes into play. And the way we're going to approach this is we're going to do what's called a proof by contradiction. The idea behind a proof by contradiction is you assume the opposite or the negation of what you're trying to prove, and then show that that assumption leads to a contradiction somehow. And that means that your initial assumption must have been false. So what I'm going to say is, since we know that there's at least one solution, we're going to say assume there exist two distinct values, x1 and x2 such that f of x1 is equal to 0, as is f of x2. So what I'm doing is I'm saying, let's suppose that there's at least two values of two real numbers that satisfy this equation, because that's what it means for f of x1 and f of x2 to equal 0. It means they satisfy that equation. So if this were true, if there's at least two distinct values, then this couldn't be true. It's the negation of saying there's exactly one real solution. I want to show that by assuming this, I'm going to end up with a contradiction. Okay? So let's suppose also, since these are distinct, x1 and x2, meaning they're different numbers, one of them has to be greater than the other. So just suppose that x1 is less than x2. Okay? Notice that the function f of x is continuous and differentiable on the closed interval x1, x2. So now I'm no longer looking at the closed interval from -1 to +1. I'm looking at the closed interval x1 to x2. And this is why I needed to assume that x1 was less than x2 so that this interval makes sense, because the smaller of these two numbers should always be on the left. This is an interval of real numbers. And why am I able to say that the function f of x is continuous and differentiable on that interval? Well, again, f of x is a power function plus an exponential function. Both of these are continuous and differentiable everywhere. And so for sure, it's going to be continuous and differentiable on a closed interval. If it's differentiable on this closed interval, then I could also say that it's differentiable on the open interval, x1, x2. And these are satisfying the first two hypotheses of Rolle's theorem. This satisfies the third hypothesis. F of x1 and f of x2 are both equal to 0, so they are equal to each other. Plugging the endpoints of this interval into our function gives me the same number. That's the third hypothesis of Rolle's theorem. So I get to use Rolle's theorem now that I've verified all three hypotheses. By Rolle's theorem, I'm going to abbreviate theorem THM. There exists a number. I've already used C up there, so I'm going to call this D. In the interval, open interval, x1, x2, such that f prime of that number, D, is equal to 0. That's what Rolle's theorem guarantees. This is the thing that's going to end up leading us to a contradiction. Because I'm actually told what this function looks like, based up, right up here where I defined it, I can find that derivative explicitly. Since f prime of x is equal to, so differentiating this is really easy, that would be 3x squared plus e to the x. Look at the two values, or the two terms that I have here. 3x squared, because there's an x squared in there, is always non-negative. It could equal 0, but it's at the very least non-negative. It's either 0 or a positive number. That's what happens when you square something and then multiply it by a positive. E to the x is always strictly positive. It can't even equal 0. Exponential functions are always positive. Since f prime of x equals 3x squared plus e to the x, and 3x squared is greater than or equal to 0, and e to the x is strictly greater than 0, think about this for a second. A non-negative number plus a positive number must be positive. Even if this is equal to 0, adding a positive number to that will give me a positive. That means that the derivative, our f prime of x, is always a positive number no matter what you plug into it. So since this is true as well as these, then f prime of x is greater than 0 for every x that you can plug into it. Thus, f prime of d equals 0, this thing that we found here, is a contradiction. That means that this can't happen. But Rolle's theorem says that it has to happen. So because we ended up at a contradiction, the only conclusion we could draw from that is the assumption that we made here has to be false. There cannot be two distinct values that satisfy this equation. But because we've proven that there has to exist at least one, that means that there can be only one. Therefore, x cubed plus e to the x equals 0 has exactly one solution. Okay? So there's similar problems like that in the homework where you're trying to prove something of this nature, and that's the idea behind it. You're going to proceed with a proof by contradiction after you've tried to apply Rolle's theorem. Now, like I said in the first video, Rolle's theorem is really not the main subject of this section. What we're really after is this thing called the mean value theorem, and the primary purpose that Rolle's theorem plays here is it provides us with a justification for a step in the proof of the mean value theorem. So I'm going to state the mean value theorem, talk about it in an intuitive kind of a way, but then we're going to prove it. So the mean value theorem says this. Let's assume f is a function that satisfies these two hypotheses. It's continuous on the closed interval, ab, and differentiable on the open interval, ab. Now notice that these are the first two hypotheses of Rolle's theorem, but we don't require the third hypothesis of Rolle's theorem. We don't require f of a to equal f of b in the mean value theorem. Okay? If these two conditions or hypotheses are in place, then the mean value theorem says that there exists some number c in the open interval ab, so some number between a and b, such that f prime of c is equal to f of b minus f of a over b minus a. Or if you would prefer, we can multiply both sides of this by b minus a to get this right here. Now, looking at this at first glance, it may not seem like anything important, but both sides of these represent something that we can visualize graphically. F prime of c is the slope of the tangent line to the graph of f at x equals c. F of b minus f of a over b minus a is slope formula for the 2 points a f of a and b f of b. So what this side is the slope of a secant line. What we're saying is that, but with the mean value theorem, is that as long as we have these two hypotheses in place, if they're in place, we can find some value c between a and b such that the slope of the tangent line at that point is equal to the slope of the secant line joining the endpoints that would correspond to the endpoints of this interval here. So here's a couple of examples showing what this is talking about graphically. Here, this black curve corresponds to a function that is very easily seen to be both continuous and differentiable. And here's the values a and b that form the closed interval ab. These 2 points correspond to x equals a and x equals b. So I could join them with a line that would be a secant line and find the slope of that line. The mean value theorem says that at some point along this curve between these 2 points here, I can find one point, at least one point, where the tangent line at that point is exactly the same slope as the secant line. Notice that these two lines are parallel. Here's another example. This function is clearly continuous and differentiable on the closed interval ab because I can sketch that curve without picking up my pen, and it's got the smoothness requirement of a differentiable function. If I join the points a and b, the endpoints corresponding to a and b down here, I get this secant line with positive slope in this case. The mean value theorem says I can find at least one number c between a and b such that the slope of the tangent line at that point is exactly parallel to that secant line, or is exactly equal to the slope of that secant line. In this case, we see two such points, C1 and C2, where the tangent lines are parallel to that secant line. The mean value theorem doesn't tell us how many values for which that will happen. It just says at least one point will have that property, where the tangent line is parallel to that secant line. So that's what this is saying. It's giving us these parallel lines here, okay? We are going to walk through a proof of the mean value theorem. And the key to doing this is we're going to assume that we have some function f of x. So this black curve is representing the graph of f of x. And then we're assuming that we're restricting our attention to the closed interval a, b. So that just kind of cuts out a little section of that function f of x. Using the hypotheses of the mean value theorem, or the MVT as we call it for short, we're going to assume that our function f of x is both continuous on the closed interval ab and differentiable on the open interval ab. So that means it would look like this. And under those assumptions, we want to prove the result of the mean value theorem. But having sketched this curve here and created the secant line that we know is relevant to the mean value theorem, I have basically two graphs here that are connected at these endpoints. I'm going to define a new function called h of x, which measures the vertical distance between a point on this blue secant line and a corresponding point on this graph of f of x. So the points that have the same x value are going to have a vertical distance between them. Okay, that's what I mean by h of x. Now this secant line will have an equation of, actually we do that down here, so I don't want to jump ahead of myself. Okay, so the equation of this secant line is going to be y minus f of a equals f of b minus f of a over b minus a times x minus a. Now, where is this coming from? This is just point slope form for a line. Okay, remember, point slope form for a line looks like y minus y1 equals m times x minus x1. So this is y1, this is x1, and this entire thing is m in the point slope form for a line. And the reason that makes sense is because, again, we're looking at this secant line. We know that this point A right here has coordinates A, f of A. So that's the point that's being used in the point slope form. And we know that the slope of this line, since we know two of the points on this graph, on the secant line, B, f of B is the second point, I can use slope formula to find the slope between those values, and this is what slope formula would give me. Alternatively, if I add the f of a to both sides, I can also say that the equation is y equals f of a plus all that other stuff here. Okay, so that is that in this form. This is telling me that y is equal to this for any given value of x. Now, even though there's a lot of stuff floating around in here, everything except for the x is a constant. Remember, a and b are endpoints of an interval. Those are constants. So this entire quotient here, it represents a constant. That's a constant. That a is a constant. X is the only variable on this right-hand side. Okay? So the function h of x that I talked about up here is equal to f of x minus all of this, because f of x gives me the y coordinate of that point right there. Okay? If this is x, then this point is x f of x. So the y coordinate of this point is f of x. The y coordinate of this point is given by this function right here. And so subtracting f of x minus this whole thing is going to give me that h of x that I'm talking about here, that distance between those 2 points, vertical distance. That would look like this. Okay? Now let's think about this function for a moment. H of x satisfies the three hypotheses of Rolle's theorem. And why is that? Well, again, f of x, we assumed, because f of x is going to satisfy the conditions of the mean value theorem, it's automatically going to be continuous on the closed interval AB, differentiable on the open interval AB. This is a constant. Constant functions are differentiable and continuous everywhere. And this is a linear function. It's a constant times x minus a. That's linear. Those are continuous and differentiable everywhere. So the difference of this function with this and with this must be continuous and differentiable on those intervals, because we have those properties of continuous and differentiable functions. So h of x has to be continuous on the closed interval AB and differentiable on the open interval AB. But in order to satisfy the hypotheses of Rolle's theorem, there's that third condition that needs to be in play, which says that h of a has to equal h of b. Okay, because we're looking at the closed interval AB, h of this endpoint must equal h of that endpoint. That's the third hypothesis. But that is easily found to be the case because if you plug a into our function, there's only two x's that were appearing in that function, here and here. So plugging a in here gives me f of a minus f of a, that equals 0. Plugging a in here gives me a minus a, that's equal to 0, times this is still equal to 0. 0 minus 0 is 0. If I plug b into that function, I get f of b minus f of a, and then I'm also plugging a b in here. Notice that I have a b minus a here, which will cancel the b minus a in the denominator here, leaving me with f of b minus f of a minus the quantity f of b minus f of a. That's something minus itself, which is also 0. That shouldn't be a surprise because, again, if you look at the graph of how we defined h of x, it's the distance between a point on f of x and a point on the secant line. But h of a would represent the distance between this point on the secant line and this same point on the graph. Notice that's where these two functions intersect. Similar over here. So the distance between the secant line and the function here is 0, as it is here. So graphically, it makes sense why we're seeing that. H of x, therefore, satisfies all three hypotheses of Rolle's theorem, so we can apply Rolle's theorem to it. Rolle's theorem says that there has to be some number c in the open interval a, b such that h prime of c is equal to 0. But what does h prime of c look like? Let's start by finding h prime of x, just the derivative of h. So let me go back to where we defined h in the first place. Here's h of x right here. Okay, if I differentiate this, f of x becomes f prime of x. Constant functions go to 0 when I differentiate them, so that's going to go to 0. And then this is a constant times a linear function with a leading coefficient of 1, so the derivative of this entire thing is just that quotient, f of b minus f of a over b minus a. That's what we're seeing right here. H prime of x equals f prime of x minus that quotient. Plugging a c into that, as I'm doing right here, will give me f prime of c minus f of b minus f of a over b minus a. And again, Rolle's theorem says that the c that we're talking about here, when plugged into h prime, will equal 0. That's the c that's guaranteed by Rolle's theorem. But if that's the case, then I can take this guy and add it to both sides, which gives me this. F prime of c equals this difference quotient. And that is what we were trying to prove with the mean value theorem. The slope of a tangent line at some point between those two endpoints is equal to the slope of the secant line. Okay? That was a lot. There's a lot to prove there. And we have some examples to look at, but I'm going to save that for part 3.